it's a pleasure to welcome Anouck Girard that has been invited to give us a talk today. I see that you slightly changed the title of the talk, so it's going to be on learning for, but on the same subject, on learning for safety to governor-based approaches. Professor Anouck Girard received her PhD degree in ocean engineering from the University of California at Berkeley in 2002. She has been with the University of Michigan at Ann Arbor since 2006, where she's currently a professor of aerospace engineering and a core faculty in the Robotics Institute. She has co-authored the book Fundamentals of Aerospace Navigation and Guidance that is published by Cambridge University Press. And her current research interests include vehicle dynamics and control, as well as decision systems. So Dr. Girard was a recipient of the Silver Shaft Teaching Award from the University of Michigan and a Best Student Paper Award from the American Society of Mechanical Engineers. She's currently a Fulbright Scholar and visiting our lab, the Dynamic Systems and Simulation Laboratory of the Technical University of Crete. And welcome, Anouck, and I'm passing the floor to you to start your presentation.
Yes, thank you, Katimera. I'm sorry that my Greek doesn't allow for me to give the whole seminar in Greek, not yet. Maybe if I come back a few more times. In the meantime, I'm very grateful for support from the Fulbright Scholarship Program, and the Fulbright Program requires hosts, and so Professors Papa Georgiou and Papa Mihail have agreed to host me in the lab, and I'm really grateful for that because there's a lot of interesting research problems, and also the weather and the food and the setting are much more beautiful than Ann Arbor, Michigan. And so thank you for allowing me the opportunity to come talk to you. Oops, there we go. All right, so to begin with, I don't work by myself, you know, I work with a team of people. And so I want to make sure that the people whose research I'm presenting today get acknowledged. And so most of what I'm going to talk about today was actually done by Nan Li and Kai-Wen Liu when they were my PhD students. Nan graduated last year. He's currently a postdoc, and in the fall, he'll be an assistant professor at Arbor University. Kai-Wen has one more year to go. And then 2 or 3 years ago, we had another postdoc, Kyung-Seok Han, who's now an assistant professor in Korea. And these 3 young men were co-advised by Professor Kolmanovsky and myself in our lab at the University of Michigan. And what we did and what we're still doing in our joint research is we're exploiting tools from control theory and optimization and artificial intelligence and trying to address decision-making and control problem for autonomy and robotics. And myself, I'm particularly interested in 2 applications, one to safety critical systems and one to multi-agent and human-robot interactions, and how we can apply the theory we developed for those systems to applications in aerospace, robotics, and automotive domains. And so this is what we do. So you can ask, you know, why do we care about autonomy? I sit at Michigan in the aerospace engineering department. Autonomy in aerospace is as old as the first vehicles that we deployed. And so the very first autopilot for aircraft was invented and tested by Lawrence Sperry in 1912. Only 9 years after the first manned flight. There's a second branch of aerospace that comes from the munition side. Autonomous missiles, autonomous bombs were invented even before that. Okay, so as long as we've been flying, we've had a history of having autonomy in the loop, in part because the pilot workload is significant in aircraft. And so we were trying to reduce the pilot's workload. For many years, the long legs of flight.
Anouck, sorry if I interrupt, just by curiosity, but these kind of autonomous systems, did they have sensors early 20th century? How could we have a feedback, or was it open loop only? Sorry.
So they had some sensors. So the first bombs were open loop.
Ah, okay.
They worked with a system from cash registered that incremented a timer until they dropped. the first autopilots had gyroscopes for sensing.
Right.
The
Thank
very
you.
first
Sorry.
one. Yeah.
Yeah.
So this is a great question, right? So over the years, we've seen a lot of change in the sensors. The autonomous parts of flight, like when you fly from the US to Greece, the long stretches have almost, I mean, for decades been done under automatic control. But for many years, taxiing, takeoff, and landing were done by human pilots. And mostly they still are. In 2020, Airbus actually did its first successful flight from gate to gate. That is autonomous taxi, autonomous takeoff, and autonomous landing using vision-based sensors, basically onboard image recognition technology. This was a first in aviation. I remember the statistic because it's easy to remember. In 2015, there were 15 incidents involving taxiing aircraft in the United States. Yeah. So for a while, the taxiing part was the most dangerous part of the flight, which is not helpful to tell people in the airplane. But so if we can make the on the ground portion of the flight safe, it'll actually be a big contribution to safety for aviation. And so quite a few people are looking at that. Okay. So why do we need it? Well, we can improve the safety, we can improve the cleanliness, that is, we can save fuel, we can reduce emissions. As we were discussing in the title slide, people are also starting to talk about urban air mobility, where they're thinking of small electrically powered aircraft that would carry 4 to 6 passengers at low altitudes, basically from rooftop to rooftop within cities. Those aircraft would have to operate autonomously because there just won't be enough pilots otherwise. Now, in space, you know, this is the aero side of the business. On the space side, for many years, we've had to rely on autonomy because it takes time to send radio signals through space. And so, for example, if you have a rover on Mars, as shown on top, it takes 20 minutes for the communication signals to go from Mars to Earth. So if the rover has a question, it sends its question to Earth. That takes 20 minutes. You have to think of the answer and decide what it is, and then send the answer back. So it's at best a 40-minute delay between questions and answers on Mars. And so we have to rely on autonomy for a number of different things. Otherwise, we wouldn't be able to operate rovers. Missions to asteroids, depending on where the asteroids are, have similar types of delays. And when you want to land on an asteroid, there's no way to do it with joystick control. It has to be done autonomously. Okay, so on space missions, there's been quite a few developments for autonomy. And then an interesting problem, the problem where we have humans and robots working together is also considered on the aerospace side of the business. For example, the top picture shows an astronaut working with the robot arm on the International Space Station. And these days, there's a lot of excitement about the possibility of having bases on the moon or bases on Mars. And if we do that, very likely robots and humans will have to collaborate to build the base and possibly do mining. So those are all topics that are relevant to aerospace engineers. Now, most of you here today aren't aerospace engineers. And so there's a question, why should we care about autonomy in automotive engineering? And one reason for that is the newspapers all tell you that it's coming. Yes, so they disagree about one. Mostly it's in 5 years. Yeah, so whenever you look at the news, it's always 5 years. In 5 years, all the cars will be autonomous. But there's no doubt that there's been significant developments in the last 10 years, and that there's, in some parts of the world, there are actually self-driving cars on the road right now. I haven't seen one in Crete yet, but in Ann Arbor, where I live, I see at least one per day. Okay, so some history, because I'm old enough to give history. This is a video that was made in the mid-1990s in California by a program called the California Path Program that involved many universities in California, but was led by Berkeley. And this is one of the first experiments that people did to prove that autonomous cars on roads were feasible. And so what you see in the video is a platoon of 8 cars, all the same. Every car in the world was a Buick LeSabre. But so there were actuators that controlled the steering wheel and the throttle and the brakes. And there was a screen for the user to input what was happening. And the cars were fully autonomous. So that's a microwave radar that was in the front that gave a distance to the car in front. So this is how we did the spacing control. That's the motor that controlled the throttle valve. I'm not sure why it had such a big space in the video and the engine. This is how many computers it took in 1995 to do self-driving cars, which is kind of amazing. And then there were several different communication systems. So the cars talked to the road and the cars talked to each other to tell each other what was happening. And to do lateral control, they relied on magnetometers. So this is a picture of a magnetometer bar or a magnetometer driving over magnets that they'd embedded in the road. Yeah. And so you can see the cars followed at 58 miles an hour because we weren't supposed to break the California law while we tested, and the speed limit was 60 at a spacing of about 1 car length. Yeah. And so for a while, if you were at Berkeley during those years in the mid-1990s, you could get a ride in a self-driving car under these very controlled conditions. And so there's no other traffic in those lanes except for the platoon. Still, it was an impressive demonstration for its time. And it was the first large-scale demonstration. They ran it for 3 to 5 years and thousands of people got rides, and people got kind of excited about the potential for self-driving cars. Okay, oops, there. So if you looked at research papers from back then, this is a picture from one of my papers. I'm not picking on anybody else, right? We had everything designed into these hierarchical layers, and there were supervision layers and coordination and regulation in vehicles. And inside each layer, we had modes with mode switches that were governed by logic. And then there was a trajectory generation module and a control law basically inside each mode. And so you had to design all of the switching logic for this and all of the transitions and all of the controllers. And so there's an example of a state machine here that's basically an automatic cruise control state machine for a project we developed. And you can see there's a lot of transitions in this model. So these are all logical conditions. Like if there's no car in front of you, drive at the speed limit. But if there is a car, adjust. And if the car is equipped with communication, do something else. And if there's a failure, do something else. And so the design of all these logical conditions took a lot of time, and the calibration was difficult. Yeah. Still, I'm in the picture. I'm in the back row about here, maybe a third of the way in from the left. We did more demonstrations of systems like this in the late 1990s at PATH. We did demonstrations with buses because they were heavy vehicles, and we were hoping the cities would, be interested. And the buses were all different, so the dynamics were heterogeneous. So all of a sudden, the world was not all just Buick LeSabres. And then the buses had to be driven by city bus drivers. So we looked at interfaces to explain to them what was happening. And right away, we ran into some real world problems. For example, the bus drivers refused to believe us that closer spacings were safer. So from an engineering perspective, there's a small energy difference if you're following very close, but with very close speed matching also. So if there's a collision, it'll be a low energy collision. But the bus drivers purely refused to do that. And so we had to drive in, as control engineers, what we'd consider the danger zone, where there's enough gap to create potentially dangerous collisions. And so we had to adapt to a lot of things. Okay. So, in the 2000s, this is what people did. And then what happened after that for autonomous cars is DARPA started funding the Grand Challenge for driving. And their focus was on infrastructure independent autonomous vehicles. Okay, so they wanted to get rid of the magnets in the road and the magnetometers for lateral sensing. And they wanted to do self-driving in a world where you had no sensors on the infrastructure. Okay? So they did this, they did it in 2004, nobody finished. In 2005, 23 vehicles competed in the race and 5 actually finished. It was a 200-kilometer race in the Mojave Desert. Now, why did the Grand Challenge matter? For 2 reasons. Okay, so first, there is some variation in the concepts about how much rule-based versus machine learning capabilities people had. Yeah, so it was the first time people really used machine learning in autonomous vehicles in real full-size practical applications. And in part, it came from the realization that all these state machines with all these mode switches and all that logic was just completely impossible to calibrate on bigger scale problems. So people relied more and more on artificial intelligence. As a Berkeley graduate, it pains me to admit this, but Stanford won the challenge. And so Stanford, CMU, and Google really started driving autonomous vehicle development, and companies from all over the world came to work with universities. Yeah, so the Grand Challenge attracted companies from the US, but also companies from Germany and Japan, and everybody kind of congregated in Silicon Valley to do automated driving research. So by 2012, Google had driven about 500,000 kilometers with its fleet of 10 autonomous vehicles. Also in 2012, states in America started implementing regulations for basically driver's licenses for self-driving cars. So there's several states in the US where it's legal to drive to have self-driving cars on the road. In 2015, Tesla accelerated the process by releasing the autopilot for its vehicles. Okay, so the bottom right picture is a picture of the Tesla autopilot in action. In the last 7 years, we've seen a lot of progress on using cameras as sensors for driving and vision-based control, and a growing acceptance of the fact that successful full driving solutions are likely to involve both some vision-based control and some machine learning. Yeah. And the two of them kind of go together because vision-based sensors are so rich that it's very difficult to process them with just rule-based type of methods. So the bottom picture is an example of a self-driving car. We see cars like this in Ann Arbor. I see at least one per day. In part because Ann Arbor is close to Detroit and a center of development, but in America, they're starting to be commonplace. Okay, so in light of all these things that are happening, what is it that we're doing in my research group? So this is a snapshot of some of the things we do in my research group. I run a lab with Professor Kalmanovsky. It's called the Vodka Lab, Vehicle Optimization, Dynamics, Control, and Autonomy. We have a website that's slightly out of date, but still, so one of our big thrusts for research is what we call autonomous systems and robotics. Yeah. And in that thrust, we deal with human-robot interaction, safety-critical control, data and learning-enabled control, and trajectory optimization. And this is kind of a roadmap of some papers. If you have questions, I'm happy to meet with you and discuss it or send you some of these papers. Today, I want to talk about topics at the intersection of safety critical control and learning, yeah? Because I think those are important topics in the age of self-driving. In this area, in the last 5 years, we've had about 50 papers, about 20 journal papers and 30 conference papers. And so I'm happy to send you some of those papers if you're curious. Okay, so why learning? Okay, so many control applications that we have subsystems that are subject to highly complex and uncertain dynamics and stringent control requirements. Okay, so difficult to meet control requirements, maybe because they operate in uncertain or unknown environments, or because they have interactions with many subsystems, or in the case of driving, because you're interacting with human-driven vehicles. So for these systems, it can be difficult to get accurate control models or control-oriented models that are appropriate for control. And it can be difficult to design control algorithms using conventional model-based approaches. On the other side of the engineering divide, we have cyber-physical systems that generate large amounts of data, including vision-based type of data, and it makes it appealing to leverage some of this data to develop controllers using data-driven or learning-based approaches. So until a few years ago, learning-based control had shown most of its promise in developing sophisticated control policies for complicated things, but mostly in the virtual world. Yeah, so for example, Google had a team called the DeepMind team that used reinforcement learning to develop control policies for board and video games. Yeah. And they developed policies for these games that outperformed the top level players in all those games. But, it's a game, right? If you lose a chess game, it doesn't have a catastrophic consequence, right? I mean, it might hurt your ego, but there's other papers, including people who developed a system that plays all of the Atari video games using reinforcement learning, right? Okay, but so in aerospace engineering, though, for a long time, there was a sense that, hey, what we're doing is safety critical. And that is, if we have a failure in the control system, people die, and it might be a lot of people that die. You know, planes carry lots of people. The airplane on this plot is undergoing what's called pilot-induced oscillations, which is a condition you clearly want to avoid, where the pilot's behavior reinforces unstable dynamics. Okay, so in aerospace type of systems, even if you have a control policy that works well in most cases, but if it performs badly in some cases, for example, those points that are in the red box on the average reward curve, this is just not acceptable. Okay? And so one problem with machine learning approaches is it's difficult to develop rigorous, explicit safety guarantees for them. And so this is what our research aims to develop. Okay? So safety mechanisms for machine learning approaches. Why you should care about self-driving and safety, because we're starting to see quite a few accidents from self-driving cars, actually. And so the first death from a Tesla autopilot happened in 2017. The driver basically died in a crash, but there's been a fairly steady stream of accidents involving self-driving cars. In 2018, this is news from Arizona, where a Waymo self-driving car struck and killed a man who was pushing his bicycle on the side of the road. Just in 2022, there were 6 deaths involving Tesla autopilots, 3 of Tesla drivers and 3 of other drivers. Okay, so we want to be a little bit careful, you know, with this implementation of self-driving cars before we ramp up the numbers to make sure that what we're doing is actually safe. This is something we know in aerospace engineering, right? When you change the interface for pilots or drivers in a radical way, there's a spike right after you introduce the new interface where things are unsafe. And so that picture shows you the number of fatalities per million departures versus years of operation. And so what you can see is for all cases, every time there was a change to the user interface, there was a spike in fatalities. And for self-driving cars, we'd really like to avoid that because the number of self-driving cars on the road could potentially be very big. And so the number of fatalities could be very high. All right, so I'm going to talk about safety, right? And safety requirements and control. What I mean by safety is kind of a broad definition of safety. Okay? So it might represent safety of the system or safety of the human interacting with the system. Okay? So for example, for aircraft, stall prevention so you don't lose lift is a safety requirement. Thermal management for batteries so that they don't catch fire is a safety requirement. And then the mathematical definition that I'm going to use is going to allow us to call things safety that may not naturally come to mind. For example, we'll be able to use it to model high precision pointing, okay, or requirements that are critical to successfully complete the mission. In spacecraft, pointing is very critical because the whole spacecraft mission depends on pointing. You need to point your sensor at something that may be very far away very precisely, and you need to point your communication antennas at Earth, and you need to point your solar panels at the sun. And so pointing requirements matter. Or we could also use our mathematical definition to model efficiency and emissions type of regulations. So really, what I mean by safety is a formalism that allows me to model all kinds of requirements and control applications. And so this picture, so at some point I have to have a block diagram, you know, and so this picture shows a typical control system with a system that's the system we want to control and a controller and sensors that measure necessary information for control. And so the system state is denoted X, lowercase x. Okay? And the way we represent the safety requirements is we're saying the state X has to be kept within a prescribed set, uppercase X. Okay, so that's our general definition for safety. Any requirement that you can set in this shape, right? U is the control signal, and practical systems typically have limited control authority because there may be range or rate limits. And so we write the control limits as U belongs to the set capital U. Then there may be disturbances or uncertainties. And we represent them by W, saying W takes values in a set capital W. And then on the left, we have this R. R is the reference input passed to the controller and defines the control objectives. Okay. And so it's usually either provided by a human operator or generated by a higher level planner. Okay. So mathematically, when I say safety critical control, I'm going to mean the problem of generating an appropriate control signal U belonging to the set capital U that guarantees that the system state X stays within the set capital X. Okay, so that's a basic definition for the problem. Okay, so in this talk, I'll talk about two different learning schemes for safety critical control. The first one is called safe reinforcement learning using the action governor. And the second scheme is called a learning reference governor. And I'm going to start with the first one. All right. So how does it work? I have papers listed below, and I can send you the papers if you have trouble downloading them. But so basically, we're going to look at safe or learning safety for systems that have machine learning, in our example, reinforcement learning algorithms. And so conventional reinforcement learning processes, you can think of it as using a learning process to train or update the controller online. However, the requirements U belonging to capital U and X belong to capital X may not be satisfied during training. So in our first approach, what we're going to do is we're going to add a scheme called the action governor between the controller and the system. And so the action governor is going to monitor the control signal U and adjust it when necessary to modified control signal U tilde. And it'll pass U tilde to the system to execute to guarantee the satisfaction of U tilde belongs to U and X remains in X. So that's what we do. We add a filter. Okay, to be a little more specific, I have to review reinforcement learning in one slide. And so conventional reinforcement learning works like this. We have an agent that interacts with the environment. Okay, so at each time step t, the agent observes a state x of t, then it chooses a control action u of t to apply to the environment. And then it observes a reward r of t. So in control language, the agent is the controller and the environment is the system to be controlled. Okay, so in reinforcement learning, as in optimal control, a policy is a map from states to actions. And so the reinforcement learning objective is to find an optimal policy that's going to maximize a cumulative reward over the long run, which is typically called the value function. Okay, so one standard way to deal with this is to do a learning procedure called Q-learning, which is a popular family of reinforcement learning approaches. And then after learning, so it has an immediate reward and an estimate of future value with a discount factor, basically. After reaching convergence of learning, an optimal policy can be extracted from the converged Q-value estimates. So one thing with reinforcement learning is it's essentially a trial and error process to evaluate and compare how good different actions are over the long run. And so in order to discover better actions, the agent sometimes has to explore new actions. And so for example, for Q-learning to converge, there's a popular strategy that's called epsilon greedy, where at each time step, the agent has a large probability, 1 minus epsilon, of applying the best action according to your current Q-value estimate, and has a small probability epsilon of applying a random action. So this is how a lot of the reinforcement learning policies that have been developed in the last few years have worked. Okay, so we have this epsilon greedy process, and it's kind of clear that during this process, there's nothing that stops you for asking for unsafe actions. Actions that cause as a violation of our safety requirement, X belongs to capital X. So in that world, a reasonable strategy is to add an action filter after the controller that just adjusts unsafe actions to safe ones. And so a number of different research groups have been working on strategies like this, including using control barrier functions or model predictive control-based approaches. But in our group, we developed a method using tools from set theory, and we called it the action governor. Okay, so action governors, how do they work? Yeah. So it's based on the online optimization problem that's shown in the bottom left, okay, where I'm minimizing how much I change the control action subject to the constraint that the next state, x at t+1, is within a safe set, x safe. Okay. There's two important features for this approach if you compare it to other approaches that are in the literature. One is we design our action governor based on piecewise affine models, and we allow both parametric and additive uncertainties. Okay. So why do we do this? It actually allows us to model a pretty wide range of cyber physical systems, linear or nonlinear dynamics, discrete mode switches, and logic-based type of specifications. And because we allow for different kinds of uncertainties, we can rely on a rough model as opposed to an accurate model to accomplish our design. It's difficult to use control barrier functions for some of these models. For example, ones that have parametric uncertainties. Okay, then the second thing that we do in our approach is we look at non-convex exclusion zone avoidance type of constraints. Do not enter this zone. Yeah. Yeah. So specifically, we consider safe regions that are defined as the complement of a set x0, where x0 can be thought of as the union of multiple polytopes. Yeah. This is a classic modeling strategy, a classic form of the constraints for problems in automotive engineering. Do not enter this, safe zone around my car, or for UAV planning problems. This is a no-fly zone, do not enter it. And so the obstacles are frequently modeled using polytopes. Okay, so in this talk, just to simplify the math, it turns out parametric uncertainties add a lot of technical complications. And so I'm just going to talk about linear systems with additive uncertainty, but the approach and all the theoretical results apply to piecewise affine models with both parametric and additive uncertainties. And I can send you the papers if you're interested. So due to the dynamics and limited control authority, the safe set, X safe, has to be an appropriate subset of the constraint set. In particular, you can note that simply setting X safe to be X in the online problem doesn't guarantee that you'll always be safe. Okay, so for example, you might be safe right now, but not in 1 second. Okay, you may not have enough braking authority to avoid rear-end collisions over one time step. So we have to think of a kind of recursive definition for safety. And so what we defined was something we called unrecoverable sets. And what they are is they're the set of states starting from which no admissible control can ensure your safety over the steps from 0 to K. So no control action that you take will guarantee that you're safe. Then we can compute the sets using the recursive formula that's on the slide. And then we define the safe set as the complement of the limit of the xk. Now, this may seem like technical hand waving, but this safe set definition that I just showed leads to several useful properties. And so in particular, we can show that the problem is well defined, it converges, constraints are guaranteed to be enforced, we have recursive feasibility, the set is maximal, and we have a way of phrasing the problems using MIQP, which makes it, which simplifies the computations, and which makes it easier to use in real time. Okay. Now, the action governor that we have can really be integrated with any reinforcement learning algorithm to achieve safe RL. It doesn't really care what the machine learning algorithm is, whether it's Q-learning or policy optimization or actor critic. What happens is, so if you look, for example, at the algorithm that's on the right, lines 6 through 10 are basically the reinforcement learning process where either you explore or you exploit. And then in line 11, we just modify the control action to the utility control action using the action governor. Okay, so it doesn't care how you came up with UT, it just keeps it safe. Okay, what does this look like for cars? So this is an adaptive cruise control problem. Our control objective, we ran it on the FTP 75 driving cycle, and we wanted to track a desired time headway of 1.5 seconds while maintaining the car following distance within a reasonable range. Not so close that we can get into a rear-end collision, but not so far that other people cut in all the time. We also had acceleration limits and a disturbance. And so if we look at the results on the bottom row, you can see that. So first, if you do reinforcement learning without action governors, the controller performance keeps improving with training, which is great. But if you look at the second plot, this is the constraint violation rate over time. And so you can see in the initial episodes, we have very high constraint violation rates, close to 80%. So there are situations where you don't want to do this. And so if you augment the system with our action governor, you can notice that there's zero constraints, constraint violations. And so the constraint violations never happen. And we also train reasonably fast. The third plot, if you're under the red line as a constraint violation, you can see that the action governor keeps you above constraints at all times. And our computation time is actually small compared to the reinforcement learning computation time. And so that makes it, we call it manageable, and we can argue whether or not it truly is manageable, but these are computations on a standard laptop. Okay. Okay, so to summarize what we do using this approach, so what we really have is we have an action governor design that's based on piecewise affine models with parametric and additive uncertainties. And after we design the action governor, you can integrate it with arbitrary reinforcement learning algorithms to realize safe reinforcement learning. And in particular, this approach can guarantee all-time safety, both during training and during operations. Okay, so one problem with this is, well, you say that's great, you have a safety design, but it requires knowing quite a bit about the system because it requires a piecewise affine model of the system, even if you allow for some uncertainties. Okay, so the question is, what if I don't have a model with bounded uncertainties? Well, then we have another method that we designed that we call the learning reference governor. Okay, and so what we do in this approach is I assume that we have a pre-stabilized closed loop system that inside of it has a system to be controlled and a nominal controller. This is actually reasonable for many real-world systems. There's often a legacy controller in the system that achieves desirable small signal characteristics. But for bigger reference signals, the nominal controller may not be able to strictly handle safety requirements or constraints such as U and U and X and X. Right? So the reference governor, which is the green box marked RG in my control loop there, is a scheme that's added between the operator or planner and the controller. And it monitors the reference command from the operator or planner, which we call R, and it adjusts it, if necessary, to a modified reference that we call V, to make sure that the closed loop response satisfies the constraints. Okay, so in general, the reference governor works based on an online optimization problem, the one I show here, where we minimize the difference between the modified reference V and the original reference R, subject to the constraint that the modified reference V and the current state X pair is within a set P, which is a subset of another set that people call O infinity. And this O infinity set is the set of all constant reference and initial state pairs, such that under this pair, constraints are satisfied for all future times. Okay, so reference governors is a standard approach in control. There's lots and lots of papers on it. There was a review paper in Automatica 2 or 3 years ago that has hundreds of references inside it. Okay. Conventional approaches for reference governor rely on explicit models of the system, either linear or nonlinear. There's all kinds of versions. Okay, but here, I don't want to do that. So this is an example where we applied reference governors to constrained aircraft control, for example. So you can see without the reference governor, we have big constraint violations in roll rate. With reference governor, we have none. Okay, so it limits the reference request in some cases to make sure that we satisfy the constraints. Okay. So what I want to do here, though, is I want to design reference governor approaches based on learning instead of relying on system models. Okay. So how am I going to do that? I heard my mouse. Okay, so I have a system. X dot is equal to f of x, y is equal to g of x and v, and I'm assuming for now that f and g are unknown. I do not have a model for the system. Okay. Instead, what I have are trajectories. Okay, so for example, y of t x naught v is the output trajectory that corresponds to initial condition in x naught and applying constant v over the interval. And then I'm going to define two different functions. Okay, so there's going to be a function capital D and a function lowercase d. Okay. And so this is what they represent. Capital D is the maximum deviation of the output trajectory from the steady state output corresponding to constant reference input V. Okay. And little d, which I assume that I can measure, is the distance of the steady state output to the constraint boundary. How far am I from being unsafe? Okay. And I assume that this is measurable. And then there's an online reference governor problem that says I want to solve this problem, find the maximum amount of adjustment delta V, such that the difference between the reference after the adjustment and the original reference is minimized, subject to the constraint that the capital D function value is upper bounded by the little d value. Okay. And so this condition is equivalent to the output trajectory corresponding to the current state as the initial condition and the reference value after the adjustment as constant, satisfying constraints for all future times. Okay, now one problem here is because we're assuming that we don't know the system model, we actually don't know the capital D function, and so we can't directly solve this problem. And so we have to learn the capital D function. All right. Okay, so we've developed a method to establish an upper bound for D. And so this method can be used for any function that's Hölder continuous. Yeah? Hölder continuity is kind of a technical thing. And so in this talk, I'm just going to assume that this beta number here is equal to 1. And so really that we're learning something that has a Lipschitz constant, that's Lipschitz continuous. Okay? But the math for the more complicated case exists in the papers. Okay, so one thing that we can note is d of the d function at 0, v0, 0, gives us an initial upper bound for all d. Okay, so we can come up with an upper bound this way. And then as we collect more data points, we get better and better estimates of d. Okay, so what we do is first we get one data point. Okay, after we collect that point, using the Lipschitz constant for D, we can construct the blue cone as an upper bound. Then we get another data point and another Lipschitz function. And then so we can construct estimates like this that become better and better with each data set. Okay. So our safe learning algorithm is shown here, or really there's two because line 11 calls algorithm 2. But this is an algorithm for safe learning for the reference governor. And so what I mean by safe learning is during the entire learning phase, I never violate the constraints. So this may be a conservative approach, but it's the approach we have here. And so it says, I never need to worry about violating a constraint either during learning or operation. And as I collect more and more data, I improve my estimate of the D function. I reduce the conservativeness of the upper bound for D, and I can gradually push my systems to the constraint boundaries without crossing them. Okay, one trick that there is we can solve the reference governor problem online, but if we restrict the adjustment of delta V to a line segment connecting V at T minus and R of T, and the norm is a quadratic norm, then we have analytical solutions for the problem, and this significantly speeds up the online computations. Okay, so there's some tricks to do this faster. Okay, so this learning reference governor requires a learning phase. So first, if you have a system that you want to control, you have to learn. And during this learning phase, we give it piecewise constant command profiles and train it. And then after the training is completed, the reference governor can safely respond to command profiles, and not necessarily piecewise constant. And there's some properties we can prove for the algorithm. We can prove all-time safety, both during the training phase and during operations. We can guarantee that the learning will converge. That is, our estimate of the capital D function will converge pointwise. And after learning, we can guarantee finite time convergence of the modified reference to the steady state maximal admissible constant command R. That is, we can guarantee that the reference governor adjusts the reference only temporarily to ensure transient safety, and that eventually the control objectives will be achieved. Okay, so what does this look like for vehicles? We applied it to vehicle rollover type of problems. Rollover problems are real things. There's many deaths in the US caused by rollover, especially for heavy trucks. There's a stretch of highway near Ann Arbor where we have at least one large truck rollover a month, especially during the winter when we have slippery roads and dangerous conditions. There's places that are just prone to rollovers. The US military also funded our research for part of this project, and they have heavy trucks operating in unknown terrains, and so they worry about rolls. Okay. All right, so what did we do? So we assume that the steering wheel angle is our reference input. Okay? And I simulate vehicle responses to steering wheel commands, or my students, using the dynamic simulation software called CarSim. And CarSim is a high fidelity vehicle model. It has hundreds of states. For implementation, we consider only 4: the roll angle, roll rate, lateral velocity, and yaw rate. This is our state vector. And then for our constraints, we use load transfer ratio constraints. And so basically they tell you the proportion of the vehicle vertical load concentrating on one side of the wheels. Okay, so the bottom 2 plots show you the learning process. So on the one hand, we have the tracking error, which decreases over the number of tracking instances over time. And then on the right, we see constraint violations. And so what we can see is there's no constraint violations ever, either during the training or once we've converged with the training. The tracking error that we have here measures the difference between the commanded steering wheel and the modified steering wheel. So having the tracking error decrease over time means you intervene less and less over time. And so that's a good thing. Okay, so what does this look like in videos? So this is what it looks like. Okay, so the red car is the car that has no reference governor, and we've given it a steering wheel profile that clearly causes the truck to roll over. Now, with no training in green, we have a reference governor, but with no training, it's so conservative with the initial estimates we gave it for the model that it doesn't turn at all. Okay? Meaning it's very safe, but it doesn't achieve what we wanted to achieve. And then as the training goes, you can see the cars get closer and closer to the edge of the rollover limit. Okay, so the modified steering input touches the constraint boundary. Okay, so that's one example. This is another example with military trucks where with no learning reference governor, the truck rolls over. Before learning, the system is so conservative that it doesn't turn, it gets stuck in the canyon. But after learning, you can see that the truck is able to follow the trajectory that was requested. Okay, so let me summarize what we have for a second. So we have an approach. It relies on a Hölder continuity condition, okay, of the response function capital D in measuring the distance to the constraint boundary to design a learning algorithm that trains a reference governor. And this reference governor guarantees all-time safety, including both in the training phase and in the operation phase. Okay, so on this approach, I don't rely on an explicit model of the system. Okay? Now, how do we get these Hölder continuity constants or the Lipschitz constant? We estimate them from either pre-collected trajectory data or from a learning phase, and it's easier to estimate these constants than to estimate the complete model. Okay? Now, you can start with conservative constants, and if you do, the learning is just slower. Okay, so the better the estimate you have for the constants at the beginning, the less conservative estimate you are, the faster the learning. Right? And so this is what those two figures show. Okay, so this approach does rely on a low level of prior knowledge of the system to be safe. But what do we do if we don't have even that knowledge available? Well, fear not. Okay, so we have another approach, and I'm not going to talk about it today because I'm running to the end of my time. And so it'll be in the slides if you want. But we have an approach that we can use that basically doesn't rely on knowing even a Lipschitz constant for the system. And so even in the case where we don't have even that information, we can design a learning reference governor. One thing that we cannot do is we cannot guarantee that the constraints are not violated during learning if you don't know anything about the system ahead of time. So this has to be a system where you're comfortable with crossing constraint boundaries in the learning phase. And in fact, for example, this is how children learn how to ride bicycles, right? Everybody crashes once, and once you've crossed the constraint boundary, you become more conservative. And so we have an algorithm for this, and if anybody's interested, I can send you the paper. The basic idea is whenever you observe that you've violated a constraint boundary, you reduce this gamma function that's part of our algorithm in that spot to make sure that you're safe. Okay, so to summarize some of the things we talked about today, we talked about safe reinforcement learning using action governors, right, where we design action governors based on piecewise affine models with bounded uncertainties. And that algorithm can be integrated with any reinforcement learning algorithm to give you safe reinforcement learning, guaranteeing all-time safety. If you don't have control-oriented models for your system, we've talked about learning for safety that rely on Hölder or Lipschitz continuity assumptions of the response bound and measuring how far away you are from the constraint boundary. That algorithm can give you all-time safety. We also have a non-safe learning version that relies actually on violating constraints during learning and using that to eliminate constraint violations. Okay, so the papers or the work I talked about is described in these papers, and I have them available if you want. Then let me just take 1 second to say, in the lab, we also do quite a bit of work on human-robot interaction and models of human drivers. And so we've developed several game theoretic approaches for modeling interactions between drivers, including level K game-based approaches, Stackelberg type of approaches, and a number of other approaches, recently some developed on based on potential games for driving. And so that's one of the other big things that we do. All right. I want to thank, once again, Professors Papageorgiou and Papamichail for inviting me. And I want to acknowledge that we've also had collaborators in industry that have supported this research, other postdocs and students, and we've had financial support from the National Science Foundation, NASA, AFOSR, Ford Motor Company, and the Automotive Research Center at Michigan. All right, thank you very much for your attention, and I'm happy to answer any questions.
Thank you, Anouck. Very interesting.
Sorry, that's a lot of information, I know, yeah.
Yes, we have like 5 to 10 minutes for questions, if there are any. So please raise your hand. So
I don't know how to raise my hand, but
okay.
Can I be?
You can start.
Anouck, thank you very much. Very impressive and very inspiring. I start with the first question. Probably I missed. You mentioned that what I want to ask, but I missed it. In several occasions, you put in a box the action governor mathematical problem in form, if I understood properly, of an optimization problem. Mm-hmm. But for all possible values of a disturbance, for example. Yeah. So did you mention how these can be solved?
In general, it can be difficult to do, but we do have some conditions where we've, okay, so it's further up.
Yeah, this is, I think, the reference governor.
Yeah, so we're in the reference governor now. So. Sorry, I have too many.
But it may also apply partly to the reference governor. I just
right. So
yeah.
so I'm not sure if this one will. So this one is very okay.
Yeah,
so,
for example,
so
here to the left.
Yeah.
Yeah. So what kind of problem is this? Because you say.
Yeah. I didn't detail it here, but what we've done is we've transformed this problem into an MIQP.
MIQP.
A mixed integer quadratic program.
Okay.
And
assuming
then,
that you have quadratic, of course, objective and linear model, but then what about the for all W?
Yeah, then it becomes considerably more difficult in some cases. So there's a number of tricks, but I cannot claim that this is computationally tractable for all systems.
But is there an exact solution to that? I mean, is there a method to produce an exact?
There is not in general. So the only times we have explicit forms are for quadratic norms and linear systems, basically.
Okay.
And so and it's not perfect. I'm first to agree.
All right, but let me ask: is there a general method, even if it is not exact, or did you have to invent the method to solve it?
We invented a transformation into a form for which there was an approximate method. Yeah.
Okay.
So
then another more general question. You said you separated, of course, makes sense between the case where you do have a control-oriented model or a case where you have no model. But we all know that control-oriented models, of course, are approximations, while safety requirements may be strict. So if you just rely on a model-oriented model to guarantee, you may not guarantee in reality. So how do you address this kind of consideration?
Yeah, so perfect safety is probably unachievable in some cases.
That's
right?
correct. Yes.
So this becomes an intellectual question that says what constitutes safe enough, right? So I think we presented a range of solutions for, I have a model and I can accommodate for some uncertainty, to all I have is a Lipschitz constant, to I don't even have a Lipschitz constant, right? But it's true that there's so the control-oriented model is one thing, but the whether or not your safety requirement corresponds to actual safety is non-trivial, right? So for example, even for rollover, it's not particularly simple to define what rollover means. So your wheels can lift off the ground and you can recover from that, right? So just using load transfer ratios for constraints may or may not be a good measure of how close you are to actually rolling over the vehicle, right? And
so probably you can use some margin depending on the criticality of the safety issue.
Right. So we use
margin to be sure to be on the safe side.
So we use 20% for rollover, for example, but it's a margin. Yeah.
Thank you, Anouck. Very good talk. Thank you.
Any more questions? So I was struggling to understand how is it possible, I mean, to have a learning without really having, without having problems with the bounds. And I mean, that's what you mentioned at the end, that you actually have a method that has gives you the possibility to continue learning, although you do have you are going out of the safety bounds. So
I'm sorry, I went very fast. But so I don't have a model, but I do assume that I know if I've crossed a safety bound. and how far away I am for crossing a safety bound. And so in a sense, that's still information about the system, and it's the information we use. And so we can either use it in a conservative way where you start very conservative and you inch towards the safety bound and you try to be safe during learning. Or if you can take risks, if you allow constraint violations during learning, for example, on cars, they have additional roll bars with wheels that they can put that basically prevent the car from rolling, even though you'd consider it a safety violation. If you allow that, then all you have to know is, hey, I crossed the safety bound here. Let me lower the upper bound right there, right? And so then you can learn faster. The problem with learning safely is it can take a long time.
Yeah, exactly. So I mean, for the second method, let's say that you presented, you need to figure out in advance some parameters. So what is the sensitivity on the selection of these parameters?
Well, it's better to be conservative than not, even though it'll make your learning longer, right? So in that set of methods, we said we never want to be unsafe. If you don't know, you take a very conservative first guess, and you learn very slowly. But then practically that may not be, people get impatient. so this may not be a workable solution for real systems and so.
Yeah, and for the examples that you presented with the trucks, let's say, I mean, that depends a lot also on the speed of the truck. So you Correct. May have different, I mean, for different operational areas of your model, you may have different results or different curves as a learning procedure.
Correct. So we use the speed as a parameter in our learning for that, and then we adapt. We learn for different speeds.
Okay.
So in Greece, people drive very fast. So I think I'd have to redo all my experiments.
Roads. We have Italians that they drive even faster. So.
Yeah, sure.
So thank you, Anouck. Any other questions? If that's not the case, Dimitri, please.
Hi. First of all, quite an interesting presentation, because we are also working with reinforcement learning, and this might be quite useful actually. So I have a small number of questions, and I understand that the X-safe region is further restricted according to a value of K, right? So that we are safe for like the next K steps. Is that correct?
Correct.
So I understand that this value of K, of course, is something that is pre-selected and determined with respect to the system that we examine upon. So like if we have a system that vehicles operate in very high speed, this K should be higher. But how does this choice affect the computational time? Like, is this linear? Is this exponential? Is there
So in optimistic cases, it can be linear. Right? In general cases, it's usually, I believe, square.
Okay.
In the case. Yeah.
Okay. Yeah. I mean, for example, if we're on a highway, then I suppose that this case should be like 5-6 steps. I mean, maybe even more.
Yeah. So we use 3 seconds ahead on the highway.
Okay. Okay. Yeah.
But those computations, so you can do some of these computations offline. But it's true that there is a number past which we couldn't do the computations. And so this works for small-ish number of states for small-ish horizons.
Okay. And the disturbance W that, I mean, for example, if we have an autonomous vehicle, the disturbance is the other vehicles, right? So I suppose that you take the worst case or something near the worst case for that computation.
So we can, because we're doing safety things, we tend to take the worst case.
Yeah, I mean, just Okay, and is it also like the size, the X is the state vector, right? Like the state that we have on the reinforcement learning modeling. So does this also affect computational time, and how much? Like if you have a state vector of like 10 variables, let's say.
Yeah, I'm not claiming it's perfect, right? So
no, I'm just asking so that I know.
So what
like...
did we run? We ran 5 state models for 3 seconds.
Okay.
And those were scenarios of 3 cars.
Sorry, one more question. What is the time step that you, like 3 seconds is how many steps ahead?
I believe it was 6.
Okay.
So I believe our time step was half a second.
Okay. Yeah,
when we do this on a PC, we can do it in about 10 milliseconds.
Okay. So it's fast.
So 4 small numbers of steps and 4 reasonable numbers of states, we can run it fast. Okay. But I absolutely agree that this would not generalize to 50 states and 20 steps ahead. Not on a PC.
Okay. Okay, it's just, you know, want to ask because I also haven't seen the paper yet, so I don't know the details of how these computations.
Yeah, I'd be happy to send you some or all of the papers. But
thank you. Actually, this could be quite appreciated. Okay, so I think that's all that I want to ask. Thanks again. Very interesting.
Any more questions? Otherwise, I would like to thank you once more, Anouck. It was a pleasure hosting you here. And in case of any questions, I mean, you all have access to the email of Anouck Girard. It's on the website as well, and you can always come in touch with her. So thanks again all for being here, and have a nice afternoon.
Yeah, thank you for your time. I'm here until May 10th. So if anybody wants to meet and ask questions, and I'll be around on campus tomorrow morning.
Nice.
Yeah.
Thank you.
Have a nice day.
Thank you. Great talk. Bye.